Welcome to Telecommunication Facts. Today we are going to learn about amplitude modulation. Let's see, what is modulation? For an example, suppose we have n number of signals which have same frequencies. So we can modulate each signal to a unique and different frequency band in the channel, then we can send all the signals over that channel without any interference. Basically what it does is, it translates baseband signals into bandpass signals. You can see in the image the result after modulation done. Why modulation? At the receiver side, if you have low frequency signals you need to have longer antennas to receive the signal. Since we can modulate the transmit signals to a higher frequency band, we can receive those signals with very short antenna lengths. Those are the clear advantages of modulation. We can classify modulation as continuous wave modulation, pulse modulation, and pulse code modulation. Continuous wave modulation subdivided into analog and digital modulation. Pulse modulation use pulse signals to modulate. We know pulse is not a continuous signal as it appears only for very short time. So it is a discrete signal after the modulation is done. PCM, pulse code modulation, is for the purpose of voice modulation. We will talk about it in another video. From this video we hope to discuss about amplitude modulation. Analog modulation can be subdivided into four types: double sideband large carrier, DSB-LC, double sideband suppressed carrier, DSB-Sc, single sideband Ssb, and vestigial sideband VSB. In frequency domain representation it is visible for us that DSB-LC contain unmodulated carrier component in the modulated signal which significantly reduce power spectral efficiency. Let's dig deep into DSB-LC. In order to modulate a signal, we need a carrier signal which have very high frequency. In amplitude modulation what we do is we change carrier signal amplitude according to our original message. This is the equation for the modulated signal amplitude. AC is the original amplitude of the carrier signal. XT denotes our original message. Mu denoted amplitude modulation index. From this image you can see how the amplitude of the carrier CT has changed according to XT. We call that amplitude variation as the envelope. There is a condition that, if you want to have that envelope according to our message, mu has to be less than 1. Then we can derive an equation for the modulated signal XCT. For the simplicity let's assume our carrier signal ZT is a sinusoid which we denote by AC cos omega t. By substituting, we can have this equation which we can use it for further analysis, such as, to calculate spectral efficiency. Let's talk about dual sideband suppressed carrier. This is very different method compared to DSB-LC because we just multiply our carrier signal and original signal in DSB-Sc. You can clearly visualize the procedure from the figure. For the sake of the simplicity, we can assume carrier is sinusoidal and obtain following equation. This is very much power efficient way compared to the previous method as there is no unmodulated carrier component. You can clearly see the difference 0I and frequency domain representation. But the drawback is that at the receiver, we cannot use envelope detector, which is a very simple circuit used to detect DSB-LC signals. So complexity at the receiver is higher as there is no envelope created in this method. Single-sideband Ssb. As you can see, only difference between DSB-Sc and Ssb is that there is a sideband filter. In DSB-Sc, there was two sidebands which contain same information. So, that is wasting power for transmitting same information twice. Sideband filter remove one sideband from the signal and only act as a filter. At the receiver side, things become more complex. Because, receiver has to do some signal processing and create missing sideband to recover modulated signal. As the second step, it has to demodulate to recover original message. Vestigial sideband, VSB. In Ssb, we need sharp filters to filter out one sideband sharply. It needs very powerful and expensive filters. VSB do not need sharp filters, it does not filter out whole sideband. So now we understand 4 types of amplitude modulation techniques. Let's talk about demodulation of amplitude modulated signals. Transmitter transmit modulated signal and then travel through the channel provided. When the modulated signal received to the destination, it has to demodulate the signal in order to recover original signal. There are 2 methods for demodulation. First one is envelope detector. In DSBLC, we discussed that there is an envelope in the modulated signal. Envelope detector trace only the envelope. So it is a very simple circuit as you can see in the diagram. All you need is a diode, capacitor, and resistor. But this method cannot be used to demodulate other types of M signals. So, DSBLC method use more power for an unmodulated carrier component, in modulation to have simple hardware in demodulation circuit. The second method of demodulation is product detector. You can see in the diagram that it takes product of modulated signal and carrier signal. Which says that, you need to know exactly what is the carrier signal used to do the demodulation at the receiver. When we consider the product of those 2 signals, there will be our original signal in the baseband. So we need a low-pass filter to remove all other noises from received and baseband signal will be the only output. That concludes this video tutorial. Please like and subscribe the channel. This is Telecom Facts. Thanks for watching.